Welcome to the iLearn Virtual Campus. Please sign up for a free iLearn membership on our website, check out our 7th annual conference coming next spring 2021, and let us know if you're interested in hosting events or leasing space on our campus by emailing campus@immersivelrn.org.
Hello, everyone. Hello, everyone. Welcome to the ISMAR 2020 conference. My name is Alan Young from the University of California, Berkeley. In the next few hours, I, together with two highly experienced student researchers, will provide a tutorial on the topic of OpenArc, tackling AR challenges via an open source software development kit. Before we start today's discussion, please allow me to first introduce our team. I'm currently the Executive Director of the FHL Vive Center for Enhanced Reality at Berkeley. The center is part of the EECS department, which serves as a central hub to promote and coordinate the teaching and education of the AR/VR programs at Berkeley. I was previously the chief scientist at the Fung Institute, also at Berkeley, helping the institute to launch 2 Master of Engineering degree programs in the areas of AR/VR and autonomous driving. Before that, I also served as the founding CTO and the COO at Aether Labs, an augmented reality startup based in Silicon Valley. I will be giving the first introductory talk about our OpenArc tutorial. The second talk will be given by Adam Chang. He is currently studying in the Computer Science Bachelor's Program and is also a lead undergraduate researcher at the Berkeley Vive Center. Then the third talk will be given by Mohammad Kashavasi, who is a PhD candidate at the Berkeley Vive Center and the XR Lab affiliated with the architecture department. He has extensive collaboration with the industry to explore the interdisciplinary topics in AR/VR and architecture, such as with Autodesk and Facebook. Of course, a software system as OpenArc could not possibly be developed with only a few people. Many students from UC Berkeley have contributed to this system. Today, we will only have time to acknowledge a few lead developers from the past, including Dr. Joseph Mankey, now at Apple, Dr. Oladapo Afalabi, now at Microsoft, Bill Zhou, now at Facebook, Will Huang, who is running his own startup at this time, and Jie-Wen Lai, who is now at Amazon, and Johan Ramakrishna, who will be graduating from Berkeley by the end of this year. 2 lead undergraduate students other than Adam we want to acknowledge also here are Wujing Ku and Alex Yu. Several funding agencies have supported our project as well, including several research grants from the ONR, Intel, and the NSF Joint Research Grant on XR, Ford University Research Grant, Siemens Labs at Berkeley, and the Berkeley Vive Center Sea Grant from our home center. Today's half-day tutorial will be divided into 3 parts. Each talk will be roughly 1 hour. The first talk will be introduction and foundation of the 3D geometry, sensing, inference, and tracking. The second talk will be focusing on SLAM and the 3D reconstruction solutions provided in OpenArc. The third talk will venture further into supporting development of deployment of high-level applications using advanced generative modeling in spatial computing. Each talk has been organized by the 3 speakers individually to have either several separate segments or 1 hour-long talk. During the segment breaks or our session breaks, most of our speakers will stay online to answer your questions. So please feel free to raise any questions during the tutorial, and we will try our best to follow up with your questions from our online interface. Also, the videos for today's tutorial will be also made available on our center's website at vivecenter.berkeley.edu. From our center website, you will be able to find our other exciting projects in the general areas of AR, VR, and AI and robotics. And you will also be able to find our educational programs if coming to Berkeley may be something of interest to you. For industrial partners, I would like to invite you to consider joining our industrial membership program, which we have provided more details on our center website as well. At the beginning of this tutorial, I think it is worth looking back in history and recognize that since Morton Heilig invented the Sensorama in the 1960s, the first virtual reality entertainment system, it has been 60 years. Later in the same century, Ivan Sutherland in 1968 created the first wearable augmented reality prototype. And AR, or more commonly known as holographic images, started to become a household name thanks to the genius creators of Star Wars movie in 1977, which showcased the use of augmented reality in a futuristic long-distance virtual meeting scenario via a piece of Princess Leia's holographic message. Today, we can say that this future world enhanced by augmented reality technologies is never more closer to reality in our daily lives. Starting from the commercialization of Google Glass that instantly captured the people's imagination, our customers primarily have 4 distinct ways to enjoy augmented reality experience today. And they are see around wearables, with Google Glass as an example. See through wearables, represented by Microsoft HoloLens. AR on smartphones, such as using ARKit or ARCore. And the escape room mixed reality type experience that mixed virtuality with reality simulations. To support AR applications to provide superior immersive experience, OpenArc is not intended to be jack of all trades, but focuses on providing a few fundamental solutions as an open source library that promotes community collaboration and reproducible research in the AR space. The areas ARKit is currently focusing on, including modeling background layout, modeling foreground objects, modeling user avatars, and optimization and sharing standards in mutual spaces. The library currently supports a selection of hardware and software. For the hardware, we have tested extensively on the 64-bit x86 processors. In the near future, we plan to further support ARM-based processors, such as the NVIDIA Jetson architecture. Interested developers may contact us to collaborate if you want to prototype an AR system using ARM processors. We are more than happy to reach out to assist you. Our library currently does not provide GPU acceleration, though, and all algorithm implementations will be based on the CPU. Also, as an open source library, we have supported a host of depth cameras, starting from very early the PND cameras. Then we added the Kinect 2 camera class. Then the Intel RealSense D435i camera. Our latest development will bring in support to Stereolabs Z2 camera and the Microsoft Asia Kinect camera. In terms of the software environment, we have provided a very easy to install 64-bit Windows binary installer of the library. On Ubuntu 18.04, you can also build the library directly from source. OpenArt will also have several dependencies, just like most other libraries. The most fundamental dependency will be the OpenCV library with the version 3.2.0 or later. Other libraries we have included, including the Eigen version 3, Point Cloud Library 1.8, Boost 1.6.4 or later, etc. Also, it is very important to note that OpenArc, being a software library focusing on low-level computer vision and depth perception functionalities, there are many other topics that greatly affect the realistic user experience in AR applications, but we will not be covering in OpenArc. If you plan to adopt OpenArc as part of a commercial system, you will probably need to support of good solutions in the following areas. And they are near-eye display and optics, AR coprocessor acceleration, custom sensors, high bandwidth, low latency communications, 3D spatial sound, and the 3D UI/UX design. However, one type of sensing modalities, OpenArc does provide strong support for depth camera. Indeed, the use of depth cameras to support augmented reality has been the consensus among many AR systems today. For example, when I worked at Aether, we were one of the first to put on a depth camera on the top of a smart AR glasses. More recently, we have seen probably the largest proliferation of depth-type cameras on Apple's iPad and iPhone lines. Let's recall first, before the rise of depth cameras, 3D structures could be inferred using multiple views of color images. This is called structure from motion, or multiple view geometry. As shown in this demo video from the paper Building Rome in One Day by Samir Agarwal and co-authors in 2010, when a structure from motion system can have access to hundreds to thousands of realistic color photos, then 3D structures in the space can be triangulated. However, the downside of a structure from motion is also multifold. For example, structure from motion depends heavily on the good lighting of the environment, and the environment also must have rich texture patterns. Also, structure from motion solves an inverse computer vision problem, and therefore is expensive to run as real-time solution to infer 3D geometry. To better support the needs of immersive AR applications to acquire accurate 3D geometry of the environment in real time, other depth sensing solutions in recent years have been used in several successful commercial depth cameras. Next, we will briefly highlight two of them. The first is called depth from stereo. For a pair of stereo cameras, usually we will assume they are well calibrated, and after calibration, we may further assume their 3D positions only differ by a translation along the x-axis, denoted as the baseline B. If we are interested to know how the 3D coordinates of an image feature is calculated, here is the equation defined by the intrinsic matrix with four coefficients, AX, AY, and CX and CY. Then from the image coordinates U and V of these images, and assume a known focal distance F. And we will know that the 3D coordinates in the unit of meters represented as a vector, 3D vector of X, Y, and Z equal to F. And this is equal to the intrinsic matrix, the inverse dot product with FU, FV, and F, where U and V are in the unit of pixel coordinates. Then look at the illustration on the right. Since the stereo cameras are aligned to only differ in position along the baseline x-axis, it is fairly easy to identify a match of two image features corresponding to the same 3D point, capital X, in space. Next, if we represent both the 3D coordinates of the first feature and the 3D coordinate of the second feature, now in the same coordinate system, O prime, and their coordinate difference only along the x-axis, written as x minus x prime, will be called the disparity. And according to the similar triangle relationship of this triangle versus this triangle, the disparity x minus x prime divided by f will be equal to the ratio of the baseline b divided by the depth z. Therefore, we have the calculation of the z value with respect to this 3D point in space. It's equal to b times f divided by the disparity. The second principle is called time of flight. The most direct use of time of flight principle is the LiDAR system, or light detection and ranging. This principle has been known to humans since the caveman era, where we know that we can estimate the distance between a human, a caveman, and a mountain by sound. And this distance between the human and the object that reflects the sound wave can be calculated by half the travel time interval times the speed of the sound. In LiDAR, this principle is used to measure the distance, but using the laser light instead of the sound wave. For example, during the Apollo 11 mission, NASA placed a lunar laser ranging experiment on the lunar surface, which then was used to accurately measure the distance between the light and between the Earth and the Moon. However, the time of flight principle also brings in the challenge of how to accurately measure the time. For example, let's assume a more modest distance of 10 meters. We know that the speed of light in the Earth's atmosphere is about 300 millimeters per second. Therefore, 2 times the distance of 10 meters divided by 300 million will be equal to about 66.7 nanoseconds. This is a very tiny fraction of time that will have required very accurate system clock. In most consumer-grade depth cameras, however, the measurement of time will be substituted and converted to measuring accumulated electric charges or phase shifts from the bounced back light signals. Due to the limited time today, we will not go further into details about how these principles are implemented engineering-wise, but we will provide a fair comparison about the quality of the depth data collected by depths from stereo and time-of-flight cameras. In the first video, we installed a state-of-the-art depth from stereo commercial system in the cabin of a car. And we want to capture how depth data may support 3D avatar virtual interaction inside the car. Notice that, to be fair, inside the car environment is one of the most challenging environments to conduct 3D sensing due to complex outdoor lighting, vehicle chassis vibration, potential high temperature, and close distance in a jam-packed small space. Let's first view the video. And please notice that on the bottom right corner, we have superimposed the RGB version of the same scene in comparison with the acquired depth data from the depth from stereo solution. From this video, we can see that usually the resolution of depth images can be coarse than typical RGB images. More importantly, depth from stereo becomes ineffective when the stereo image source becomes saturated by sunlight or underexposed by low light. Finally, depth from stereo usually has limited range in short and long distances, which will create invalid depth data shown as many black regions in this video. In contrast, invalid pixel values do not exist or very rare in typical RGB images. We can compare the previous video in the same scene now captured using a Microsoft Asia Kinect camera. Asia Kinect uses time-of-flight principle to measure depth. Compared to the previous example, we can easily see that Asia Kinect in outdoor environment provides much better signal-to-noise ratio. And the generated depth images are much sharper than the depth from stereo system. Second, Asia Kinect is affected less severely by the sunlight and also works well under low light condition thanks to its onboard modulated time-of-flight light emitter. But same as almost other depth cameras, time-of-flight cameras also generate invalid depth pixels, already shown in the image, due to its own distance limitation. To summarize, when we design algorithms using depth cameras, the algorithms must handle the following situations specifically. Number one, we will need to handle coarse or more noisy depth data compared to RGB images. One common practice is taking smoothing of adjacent pixels in the 3D matrix space. And second, we will need to handle the existence of invalid depth pixels. In matrix representation, those invalid depth are usually denoted as zero values. As such, including zero depth pixel values in most of our calculation will be wrong. The correct way will be to write in your code to exclude these invalid pixels from the calculation altogether. In addition to the three depth inferencing approaches, there are two other popular used approaches, and they are called structured light and depth from defocus. Now let's put the 5 approaches in one table and go over under what circumstances we should consider or not consider these 5 approaches. First, structure from motion. This is the classical solution from computer vision. It is widely used in real-time 3D localization and visual odometry to estimate R and T, rotation and translation, of the corresponding camera sensor. And it also works well in large-scale reconstruction problem from big data photo libraries. Depth from stereo is good for outdoor applications and has good trade-off between accuracy and cost. Its measurement tends to be more accurate on texture regions, such regions can be actively created also by an onboard light emitter as well. On the other hand, structured light is more suitable for indoor applications, and it is also low cost. However, under the same scene conditions, depth from stereo and structured light both tend to be less accurate compared to the time-of-flight solution. Then for high precision applications, the usual choice will be time-of-flight sensors. And they are particularly good for both 3D localization and dense 3D reconstruction. However, time-of-flight systems are more expensive and demand higher power compared to most of the other systems. And then they don't always work under the sun and need special design and hardware to work accordingly outdoors. Finally, if our camera mechanism remains conventional, we can still estimate depth using depth from defocus approach. It is commercially used to enable automatic lens focus adjustment for camera lenses, but it is not a good choice for 3D reconstruction and scanning in AR applications, because recovering the defocus or the blur function from images typically does not return a dense depth map, but only a sparse map concentrated around only the textured regions. Now we will pause our talk here and see if the audience have any questions. After that, we will proceed to discuss the second part of this talk. Hello everyone, welcome to the ISMAR 2020 conference. My name is Alan Young from the University of California, Berkeley. In the next few hours, I, together with two highly experienced student researchers, will provide a tutorial on the topic of OpenArc, tackling AR challenges via an open source software development kit. Before we start today's discussion, please allow me to first introduce our team. I'm currently the Executive Director of the FHL Vive Center for Enhanced. Hello everyone, welcome to the ISMAR 2020 conference. My name is Alan Young from the University of California, Berkeley. Hello everyone, welcome to the In the first segment of this talk, we have mentioned that depth cameras may generate invalid depth measurements. In the first segment of this talk, we have mentioned that depth cameras may generate invalid depth measurements. When we project the depth information onto the 3D point cloud, it leads to many unique challenges in 3D geometric data understanding. Some of the challenges we will list in this page to start our second half of the technical discussion. These challenges include inferring 3D using minimum number of images, accurate dense reconstruction for virtual augmentation, complete 3D model without holes, shareable and editable space models for multi-users, augmentation of human users as realistic avatars, and finally, privacy and standards using shareable 3D data. Today's tutorial will provide to our audience actionable information to address the first 5 challenges. But although the last challenge is equally important, we will not touch this topic in this tutorial because any solution to privacy and standards when sharing 3D data will go beyond the scope of a software library such as OpenArc. First, let's focus our discussion on the challenge of automatic shape retrieval and the completion. Since earlier we have emphasized that RGBD sensors tend to obtain incomplete models of objects from 3D space. For instance, when we use a time-of-flight camera to acquire a 3D model of a chair, as rendered on the right, some part of the object in space then can be easily missed from the acquired 3D model. This may be due to a variety of reasons, such as measurement noise, occlusions, distance limitations, or material properties of the object. Then our task on such incomplete data will be to complete the 3D objects for actual virtual augmentation. If we look at this problem from 30,000 feet, there are 2 very well understood approaches. The first approach is to modify the noisy point cloud with the expectation to clean up the data and have the point cloud to match with the ground truth 3D model. For instance, the well-established iterative closest point, or ICP, Hopf transform, and the RANSAC all belong to this approach. However, if we are familiar with these algorithms, you may recall the following drawbacks. Number 1, in AR applications, our 3D model knowledge will never be exact to match real object point cloud. For example, we may have a 3D model from the chair category, but we cannot possibly have exact models for every type of chairs. This fact has been established as a key sticking point even in image classification challenges. Second, 3D point clouds are unordered and randomly sampled. Therefore, it is difficult to solve for exact point-to-point correspondence between two point clouds. Number three, even if we can solve for a stable matching for rotation and translation, the transformed point cloud will still retain scanned holes, and the above algorithms lack the information about how the scanned holes should be compensated. Therefore, in 3D shape completion problems, using deformable CAD models are becoming more popular for real-world scenarios. The typical goal of using deformable CAD models, as we illustrated on the right, is to define objective functions and effective operators to deform a representative categorical 3D CAD model to fit the noisy point cloud observations. Advantages of this approach are manifold. Number one, the algorithm preserves the noisy measurement, but choose to operate on cleaned model data, which will be better conditioned to apply any deformation. Number two, deformed model tends to automatically fill up holes from the measurement data. And number three, and most importantly, using deformed CAD models does not require exact matching of the model shape with the real object shape. Next, let me present a short journey about our experience in finding a good solution to match 3D object shape and simultaneously complete missing shape point cloud data. To begin, we need to choose a good CAD model database with sufficient semantic annotation. We have chosen ShapeNet from Leo Gibas Group at Stanford as our reference library, which is a richly annotated large-scale dataset of 3D shapes. Due to the fact that a CAD model library does not intend to represent exact shapes of all the objects in the same category. For example, on the right, ShapeNet enrolled different CAD models under the same chair category. But only when those 3D models are sufficiently different in their shapes, then they will be enrolled in the ShapeNet. Therefore, these models are in the library are typically normalized in a unit cube instead of preserving their real size. So when using these models, there is one additional dimension of unknown scale that we need to estimate and rigidly transform into. In addition to the model categories, ShapeNet metadata also provide annotation for where is the upright and from directions, if an object contains parts, and if an object contains symmetry, etc. Our investigation into this problem started with trying to reproduce another paper from Leo Gibas' lab called Learning Representations and Generative Models for 3D Point Clouds in 2017. In this paper, the authors proposed an autoencoder network to estimate a latent representation, H, of the deformed CAD model space, which minimizes the reconstruction error, where the FH is the 3D shape reconstructed by the decoder portion of the network based on the latent variable H, while H is also estimated from the input noisy point cloud data to represent the deformed CAD model space. Therefore, H is called the latent code for representing a family of input shape data. In the paper, the authors gave a few validation examples, such as being able to complete point cloud with missing parts, and being able to use H as feature vectors for shape classification. However, in our experiment with augmented reality immersive applications in mind, we found that the proposed objective function tends to generate deformed mesh models that contextually not plausible or visually not pleasing, such as one example provided on the right. This type of results may very well have minimum reconstruction error and also may correctly identify the right category, in this case as in the chair category, but it does not fulfill our goal for augmented reality applications to provide visually pleasing 3D complete shape from the point cloud with the missing data. To address this problem, from our research, we believe that introducing an intermediate continuous function of sign distance function can successfully improve the quality of this shape completion approximation. For those of you who have not used sign distance function before, it is an extension of the definition of a level set. For a shape S, a sign distance function can be evaluated at any 3D coordinates x. And it is simply defined as if x is inside the shape S, then its sign distance function is negative shortest distance from x to the boundary of the shape S. If x is outside the shape, then its sign distance function is the positive value of the shortest distance, d. It is easy to check that from the definition, sign distance function is a continuous function. The magnitude of its gradient is always equal to 1, and on the boundary, this gradient of the sign distance function is equal to just the normal vector. Then in the paper published at the CVPR 2019, Jong-Joon Park and co-authors proposed a deep auto-decoder network to approximate not just the point cloud, but the continuous sign distance function, phi, that is compatible with a category of shapes, such as chairs, tables, cars, etc. The use of this latent shape variable is very important, because if we do not simultaneously optimize this latent shape variable, then each autodecoder network will only correspond to a fixed shape of CAD model, and it loses the generality to be deformed to approximate a category of different shapes. With the added input dimension of this latent shape variable, we can then use training shapes to optimize the autodecoder network parameters, such that given a training shape S, there exists a one-to-one correspondence between the Z value to the training shape S and its corresponding sign distance function. For instance, let's go over one way to optimize both the autodecoder network and the latent shape variable Z. During the training, we can assign n distinct codes from Z1 to Zn for the n distinct shapes from S1 to Sn, such that the same autodecoder network can minimize the difference between the given shape's sign distance function and the network's output value. Then during the testing, of course, the network parameters now will be fixed. An algorithm will solve for the optimal Z in its latent space that may also minimize the observed point cloud's average sign distance function. And we can see that when the deformed CAD model is an exact fit on the observed point cloud, then the total difference function should be very, very small, close to 0. That's the objective function that we are trying to minimize. Without going into more details about the implementation, which is provided in one of our papers in 2020, called Extending Deep SDF for Automatic 3D Shape Retrieval and the Similarity Transform Estimation. We can summarize our proposed joint shape retrieval and transform estimation algorithm as follows. Number one, the shape completion problem is formulated as finding the optimal Z star given trained autodecoder network parameters and the partial observation point cloud from x1 to xk. The network can approximate any number of points in unordered fashion, which was a major sticking point for optimizing in point clouds. In fact, the autodecoder network can generate a continuous sign distance function for any 3D point, not just at the sampled point cloud that could be incomplete. Number four, evaluation of the sign distance function does not require the encoder part. Once we recognize that, then during the training, we also do not need to train a set of deep neural network parameters for the encoder network. Potentially can make the optimization faster and more stable. Finally, we said the most important property of the estimated sign distance function is that it represents deformable CAD models. The model boundary of the deformed shape is simply the zero set of the estimated sign distance function. This zero set from the continuous sign distance function will yield object surfaces that are more complete and visually more pleasing than compensating the noisy point cloud or its mesh model. In this page, we will show a comparison of compensated object shapes using some test shapes on the left. The red color indicates measured samples, and the gray color indicates estimated deformed CAD model superimposed. And we can see that our proposed method fits a lot better than the existing other methods, both for completing the missing data and for estimating the optimal pose and scale of the CAD model in 3D space. And you can compare the quality of each of these 4 example scans. The last topic we will discuss in this talk is about 3D avatar modeling, which is another function that is very important for realistic virtual immersion experience. In the literature, most people are familiar with the 3 main directions, namely using skeletal model, using fully articulated model, or using deformable avatar models. In particular, when affordable, deformable avatar modeling is preferred, including in the applications of video games, social media, telepresence, and the human simulator for medicine training. In the literature, tracking deformable human avatars can be achieved by either an offline multi-camera system to capture all the light field from 360 degrees. However, for most mobile AR applications, it is more desirable to use solutions that are real-time and only require a single camera. So this is the scenario we are interested in OpenArc. Then we can summarize the existing literature in 3 directions, including template-based, based on body skeleton or silhouette, model-based, such as the simple model, and the freeform, such as Kinect Fusion or Dynamic Fusion. In OpenArc, we have chosen a hybrid model aiming for extracting a low-dimensional model, fast solver, and model fusion. Using low-dimensional models increases estimation robustness and speed for working a low-dimensional space. Most of our AR systems have limited compute budget, so the existence of fast solvers will help with the real-time performance on low compute devices. And finally, our model fusion will combine both 3D depth plus 2D RGB image information for enhanced realism and robust tracking. First, let me play a short demo video created by our lead student researcher, Bill Zhou.
In this demo, we will show a model-based, fully deformable human avatar reconstruction system based on a single RGB camera feed. This will be available as a module in OpenArt, which will help AR devices better understand the human body and its interactions with other real-world objects. We begin with a linear, low-dimensional model of the human body called a symbol. The model consists of joints and shape keys, which can adapt to any body type. Given a single RGBD observation, we attempt to fit a parameterized model to the depth image. The model-based tracking allows us for missing points. Gangnam Style. Gangnam Style. Gangnam Style. Gangnam Style. Hey, sexy lady. Gangnam Style. Hey, sexy lady.
The real-time avatar tracking is achieved by using fast solvers to minimize the following joint models. First, we will be minimizing the standard ICP error between the measured point cloud and the physical model. And second, we will minimize the body joint prior. This is done by running a neural network model. Finally, we also minimizes a post prior, which is a learned probabilistic model based on human pose knowledge, namely which body pose configuration has high probability and which configuration has low probability. In particular, in our algorithm, we have adopted open pose as a neural network model to anchor the joint positions of our video streaming data. Due to the fact that our algorithm was developed initially based on the Intel D435 camera, its depth signal could be quite noisy, as we have shown in the video and also a screenshot in here. So, directly optimizing a deformable avatar model in the depth map data will be prone to error. To mitigate this problem, we used the correspondence between the depth image and the RGB image, one-to-one, pixel-to-pixel correspondence. And then we first use open pose to identify the best skeleton joint positions in the RGB image. Then feeding the deformable avatar model in the corresponding depth data positions can be initialized from a good guess. Then our algorithm in real time will iteratively retrieve a new frame. Upon receiving its RGB image, a joint prior will be fitted in the image space using the open pose. These joint positions will be used to minimize the post-prior error and the ICP fitting error. For more information, please refer to our code in the OpenArc repository. Okay, this will complete our first talk. And if you have any questions, we are happy to continue to answer your questions for the remainder of the time.
Hi, welcome to OpenArc's ISMAR 2020 tutorial. My name's Adam, and today I'll be giving an introduction into two key concepts in AR/VR, SLAM and 3D reconstruction. OpenArc is an open-sourced augmented reality SDK that will allow you to rapidly prototype AR applications. It was founded at UC Berkeley in 2016 with the mission of offering core AR functionality to developers for a multitude of devices. You can view our project website at the first link, and the source code is available at the second link to put to use in your own projects or contribute. On the right is a picture of my research partner Moonwan and I at the Jacobs Hall Berkeley Winter Design Showcase. Some of the core AR functions forming the foundation of AR/VR today are listed below. At OpenArc, we have developed and are currently developing systems to provide each of these functions. Today, I'll be focusing on two of the functions that OpenArc provides: camera localization and 3D reconstruction. First, SLAM. SLAM stands for simultaneous localization and mapping. Localization refers to the process of determining the current position of the camera with respect to some representation of the world. Mapping refers to the process of generating a representation of the world from a sequence of camera frames. These two problems are deeply intertwined. Some of the largest advances in industry AR/VR are powered by advances in SLAM. Of note are standalone VR headsets and in-picture AR mobile applications such as Google's 3D Object Viewer and Pokemon Go's AR Plus Pokemon capturing scene. What they share in common is the ability to anchor virtual objects into reality. When you move your head inside a VR headset, the expectation is that virtual objects on the display remain grounded as if they were truly there in reality. This requires a frame-by-frame estimation of the camera's position at all times. The algorithm behind this is SLAM. Reading the first sentence from the Wikipedia article on SLAM, simultaneous localization and mapping is the computational problem of constructing or updating a map of an unknown environment while simultaneously keeping track of an agent's location within it. The GIF on this slide illustrates an example of a visual SLAM, which uses RGB and depth images from a video feed to track a camera's 6 degrees of freedom pose over time. These 6 degrees of freedom refer to XYZ position, pitch, roll, and yaw, rotation. Notice the yellow and green dots in the video feed. These are called key points, and they are vital to the operation of visual SLAM. In general, a SLAM framework is built with the following 4 steps. First, initialize a map of landmarks. By landmarks, I'm referring to 3D key points and their associated features. Second, receive a new frame from the camera and estimate the change in position and rotation of this frame. Third, extract landmarks from this new frame and add them to our map. Finally, optimize the pose estimation and optimize landmark positions. This process can continue indefinitely, and the map continuously expands as new frames come in. So, what are the building blocks of SLAM? Today, we'll be talking about 5 building blocks of SLAM. First, key points and descriptors. Second, map representation, how SLAM stores the map of the world. Third, frame-to-frame transformation estimation. How do we estimate the pose of a camera frame given this map of the world? 4, loop closure. 5, alternative sources of data, such as inertial. Key points, or features in the case of SLAM, are specific points in an image that satisfy these key conditions, allowing them to be used for SLAM. They are usually corners or pieces of patterns that can be identified and tracked with ease. They need to be salient, meaning they are unique points detectable from different positions and different image frames, and able to be matched between frames. This means if I take an image of a building from one angle, and then reposition and take an image of the building from a different angle, I should be able to find key point pairs between the 2 frames. They need to be describable, meaning each key point needs a unique label. Creating this label is what transforms the point from a key point to a feature. One desirable quality is that the key points should be rotation and scale agnostic, as rotating the camera or moving farther or closer from the object should not influence whether a key point is detected and matched to itself in a previous frame. Lastly, they need to be of relatively small quantity, as brute force key point matching requires ON squared time, checking each key point in a new frame against every key point in a previous frame. Here are two examples of key point detectors and descriptor extractors. On the left is SIFT, short for Scale Invariant Feature Transform. SIFT is an early form of scale and rotation invariant feature extraction. It first detects potential key points using sliding windows of different scales. It then assigns an orientation to the key points based on a summary of the neighboring pixels. Finally, a feature descriptor is created from a 16 by 16 pixel area surrounding the key point. BRISC, short for Binary Robust Invariable Scalable Key Points, is a more recent algorithm. It achieves competitive and sometimes better results, but with faster computation time. The image depicts the sampling pattern that BRISC uses for generating a feature description. In their paper, they report a 3 times speed increase when finding correspondences between two images over older algorithms, such as SIFT. Correspondence matching being one of the more intensive portions of the SLAM algorithm means this speed increase is greatly appreciated. Once we have these key points, we can perform key point matching. Using these correspondences between two different images, we can now move on to finding the transformation between these two images. Once we have established these key points, or landmarks, we have to maintain some form of global map inside SLAM. One example implementation of this global map is a list of keyframes. Keyframes simply refer to images with their associated features and position. Using these keyframes, we can perform loop closure when re-encountering a scene from an older frame. Another implementation of this global map is a list of circles. Circles, or surface elements, are small disks that dot the surfaces of objects in our scene. By using circles, we can also maintain a map of the scene that we've seen so far. The map is necessary for both estimating current poses as well as performing loop closures. The next key concept required for SLAM is frame-to-frame pose estimation. Pose, or transformation estimation, refers to the relative translation and rotation between two image frames. The transformation estimation is performed using key point correspondences between any two frames. This is an optimization problem and can be solved in different ways. At its most basic level is the perspective and point algorithm, which, given a number of key point correspondences between two frames, can estimate the transformation between them using simple geometry. This algorithm, along with others, assume that the points recorded belong to a rigid body, meaning their relationship to one another in 3D space remains the same between frames. Another way to solve this frame-to-frame pose estimation problem is with an extended Kalman filter. By maintaining a state vector with all current observations and landmarks, the extended Kalman filter can be used to estimate the current position of the camera and minimize error. Another key part of SLAM is loop closure. Loop closure seeks to answer the question, what happens when I come back to the same place I've been before? What do I mean by this? Imagine walking around a building. You start on the northwest corner of the building and slowly work your way around the building. Once you've finished a circle, you come back to where you began. However, due to SLAM drift, which is inevitable due to noise, we find that our estimated trajectory takes us to a position different from our starting position. Loop closure refers to the algorithms that detect coming back to the same place, as well as being responsible for optimizing the camera's trajectory such that the current camera pose realigns with our starting position. One such implementation of loop closure goes as follows. We maintain a map of keyframes and their description. This description is called a bag of words. Then, with every new frame, we compare it to all previous frames and look for matches between these bags of words. If we detect a loop closure, we optimize the global map to match our new observations. The way frames are described is using an algorithm called bag of words. The idea behind bag of words is to form a description of a frame using a vector of words. Then, the similarity between any two frames is how many words two frames share in common. The words assigned to each frame are created using patches of the image. If two images contain a similar region inside them, that similar region will be assigned the same word in both images, increasing the similarity between these images. The final part of loop closure involves optimizing the global map. One way of doing this is by iterating through a global map of keyframes and optimizing them one by one. We know the current frame's transformation to close the loop. We can then use the updated landmarks to calculate the optimization of the previous keyframe. We can continue to do this iteratively until we have optimized our entire map. Another way to optimize the global landmark is through continuous bundle adjustment. Bundle adjustment seeks to reduce the overall error of our system, the predicted position of all observed landmarks, versus the actual position of all observed landmarks. Bundle adjustment is much more powerful, but oftentimes is run after the SLAM algorithm is terminated as a final polishing, rather than continuously during SLAM due to its computation cost. As the map grows in size, the number of factors to optimize increases in size very quickly. One final augmentation to SLAM is provided via alternative sources of data besides just visual. In this case, inertial. IMUs, or inertial measurement units, measure acceleration. One common place you can find them is inside your mobile phone, used for orientation measurement and other purposes. Inertial data is very helpful for a SLAM algorithm, as understanding the direction of acceleration more tightly bounds the transformation between two frames. Now that we have these fundamental building blocks of SLAM, we can see how they come together to form a fully fledged SLAM algorithm. In general, SLAM is broken into two parts, with the front end involved with tracking the pose of the camera in real time, and the back end optimizing the global map of landmarks. In code terms, these are two separate threads running side by side. Modern-day SLAM algorithms pick and choose a front end and a back end in order to achieve the desired results of speed and accuracy. SLAM is an ongoing point of research, and several projects are striving to provide faster and more accurate pose estimation results. OrbSLAM is one such open source project. It is a solely visual system with no inertial data used in its SLAM algorithm. Both BADSLAM and Elastic Fusion use both circles and keyframes as their global map representation. BADSLAM features continuous bundle adjustment as its back end. OKViz features a visual inertial odometry system. This means that along with visual data, inertial data is used to perform SLAM. Adding inertial data creates a much stronger and more robust visual inertial SLAM system. Modern SLAM algorithms and the ones used in industry all rely on this additional inertial data for stronger camera position estimation. In addition to higher accuracy, having an inertial measurement unit to fall back on during visual failure cases is always welcome. A major difficulty is the higher hardware requirement, needing synchronized IMU and cameras. Modern SLAM research focuses on inertial SLAM. Visual inertial SLAMs can be divided into two separate classes, loosely coupled and tightly coupled systems. Loosely coupled inertial systems use the IMU data to simply estimate orientation and pose, for example, using the direction of gravity as a heuristic. Tightly coupled inertial systems add the IMU data as part of the optimization formulation itself. Modern research has leaned towards a tightly coupled SLAM solution for better results. OpenArc's SLAM system puts all these components together into a fully fledged SLAM system. It's built on several existing localization projects, OKViz, short for Open Keyframe-Based Visual Inertial SLAM, and DLoop Detector, a loop closure detection library. It is capable of performing real-time estimations from a variety of different cameras, using RGB images, depth images, and IMU data to accurately generate its predictions. The underlying OKViz localization system uses a tightly coupled visual inertial odometry system for its pose estimations. The loop closures use the iterative keyframe method described earlier, where keyframes are optimized using keypoints and ransack. The OpenArc SLAM team is constantly in flux as Masters of Engineering students come and go as the years go on. The lead graduate researcher behind OpenArc SLAM is Joseph Menke. The rest of the students listed here took part in developing OpenArc SLAM as part of their Masters of Engineering work in the last few years. Visit our website to see a full list of contributors to OpenArc as a whole. Some of the current work on OpenArc SLAM involves dealing with the failure cases of SLAM. Two common failure cases are scenes with minimal features, such as the image on the left depicting a blank white wall, and scenes with repeating features, such as the image on the right containing a row of lockers. SLAM's reliance on good key points fail in both these cases. On the left, there are no features to extract from the image, and on the right, multiple images will return the same key points. In these failure cases, having an inertial measurement unit provides a rough estimate of the camera's location. However, due to the nature of measuring position indirectly via acceleration, noise in the measurement explodes very quickly, leading to divergence within a few seconds. The solution to this issue is an algorithm that generates new localization maps upon detection of a failure case, and only attempting to re-merge with an old map prior to the loss of localization after the failure case is gone and strong features have returned to the scene. With this solution, OpenArc SLAM can run in larger and more diverse environments, robust to failures and able to self-correct via both loop closure and merging of maps when visual SLAM failures occur. To summarize SLAM, we have 3 steps that are performed continuously throughout the running of a SLAM application. A map of the environment in the form of keyframes and keypoints is constantly being added to and generated as more of the real scene is explored by the camera. The camera is localized at every frame within this map of the environment. Finally, loop closures are performed when returning to a previous point in the scene, re-optimizing the position of the camera and the map of the environment. Next, we will peer into OpenArc and see what allows the SLAM system to run and provide real-time visual inertial SLAM using a variety of different cameras. There are quite a few open source libraries that OpenArc builds upon to create the system we have today. First, we have OKViz, the foundation for the SLAM algorithm. It performs localization of the current frame, as well as maintains the keyframe map representation of the scene. D-loop detector is used to detect loop closures between the current frame and a keyframe in the keyframe map using the key points extracted and the bag of words extracted from each frame. Brisk is the key point extractor and descriptor used to featurize images. Eigen, Serres, and sweet sparse are all linear algebra solvers used throughout the system to quickly find linear solutions. OpenGL is used to visualize the result of the algorithm. DBOW2 provides the bag of words functionality for loop closure. Finally, PCL, or Point Cloud Library, provides functions such as 2D to 3D projection of depth images and ransack PNP. The two major frame data types in OpenArc are the map keyframe and the multi-camera frame. The map keyframe is used by SLAM in order to generate the keyframe map of the environment. This is reflected in the type of data stored, the position of the frame optimized by SLAM, as well as the key points and descriptors extracted from Brisk in order to be matched with current camera frames for loop closure. In terms of SLAM, this is the back-end data type. On the other hand, the multi-camera frame is the front-end data type. When new frames are retrieved from the camera, they are constructed into a multi-camera frame, and SLAM estimates the current camera's pose. If the current frame becomes a keyframe, a map keyframe is constructed from the pose and the extracted features from the frame. A few key objects for SLAM inside OpenArc are listed here. OKViz SLAM system is the main API for OpenArc's SLAM system. New camera frames and inertial data are pushed into this object, and pose estimations are outputted. Sparse map is the object maintaining a map of keyframes for use of detecting loop closures. There are actually several sparse maps stored at any given time, reflecting the loss of localization SLAM fix implementation, in which multiple maps are created until they can be merged back together. The camera class is an abstract class which wraps the specific camera API in order to pull new images and new IMU data. GLFW Manager manages the GUI of our SLAM system, useful for displaying the results of either SLAM or real-time 3D reconstruction. The SLAM demo has the following structure. First, you initialize a camera object, specific to whichever camera you are using to run OpenArc SLAM. Currently, supported cameras are the Intel RealSense D435i and soon to be Stereolabs Z2. Then, the SLAM system and GLFW Manager objects are instantiated. Callback functions are passed into the SLAM system, called either when a new frame estimation is outputted, a new keyframe is outputted, or a loop closure is detected. Finally, the main loop can be run. At each iteration, a new frame is pulled from the camera, as well as an inertial measurement unit measurement. These are passed into the SLAM system, and when the SLAM system is finished estimating the pose of the current frame, the appropriate callback functions are called, and the output of the system can be visualized. The SLAM demo visualizes a 3D axis anchored at the starting position of the camera upon initialization of the SLAM demo. Recent work by OpenArc's SLAM team, Jiewen Lai, Chi Wu, and Johan Ramakrishna, involved creating an offline version of OpenArc SLAM. The system is capable of recording the necessary data from the camera class in OpenArc during real time and saving it to a folder structure. Then, the data can be reloaded at any time and SLAM run. This was very crucial, especially during contemporary circumstances, as work from home has forced team members to collaborate across the world. Test sets need to be portable so that issues can be recreated consistently. The necessary data required to run SLAM in offline mode are listed here. First, we need image data extracted from the camera in order to perform SLAM. Next, we need time-stamped IMU data, as considerations have to be made due to the IMU and camera frames running at different frequencies. Timestamps are required for the system, as the time between frames is considered when estimating their relative poses. Finally, camera intrinsics are required to accurately project depth images back to their 3D coordinates. The final result is a SLAM demonstration where a set of 3D axes are anchored to the start position of the camera in 3D space, and the user is capable of placing objects at will throughout the scene, which will also remain anchored in 3D space, thanks to the estimation of the current camera frame at all times. The code runs at 30 frames per second on PCs, laptops, and tablets. Alternative visualizations, such as a bird's eye view of the trajectory map, are available as well. Hi. Now that we've built a foundation for SLAM, we can talk about 3D reconstruction. 3D reconstruction is the process of capturing the shape and appearance of a scene or object. 3D reconstructions can be created through a variety of different technologies. In the case of the reconstruction here, we used a sequence of RGB and depth images, estimated their relative poses using SLAM, and generated the 3D reconstructions by projecting the points from the images back to 3D space. Google Earth recently started adding 3D reconstructions to its views of the world. Using many observations of the same area, the 3D position of all the points can be derived and a 3D reconstruction created. In general, 3D reconstruction comprises of the following parts. First, you need some sort of point cloud data. This could come in the form of a sequence of RGB or depth images from a camera, or a 360-degree LiDAR data from a 3D scanner. Depending on the type of data, additional steps are required before any sort of 3D reconstruction can be extracted. For instance, position of all the images. Next, we need to perform integration, or merging the images together. Then, we can perform mesh extraction, pulling out vertices and triangles from point cloud data. Finally, additional improvements can be made to the mesh, such as simplification and texturing. First, pose estimation. SLAM allows us to align the images into a common space, such that we can integrate them successfully. Once we know the position of a frame, we can combine it with all the other images we've collected so far into some data structure. Once we have a pose estimated image, we need to convert the depth image to a point cloud in 3D space. Assuming we're using a pinhole camera, we use the intrinsic matrix to project pixels from the image to 3D space. The intrinsic matrix is unique to each camera and is a projection matrix from a pixel on the image plane to a 3D ray. We then use the depth data to find the actual position in 3D space. Once we have these point clouds, we need a way to integrate them or merge them together. A naive way of doing this would be to simply combine them into a larger point cloud containing the points from both smaller point clouds. However, this loses the context in which these point clouds are generated. The points are noisy measurements of a common object. Therefore, it is more effective to merge and average the observations of different frames to develop a better representation of the scene. When it comes to integration and a geometric representation to integrate frames into and create a 3D reconstruction from, there are several different approaches, of which we'll talk about two. One uses a list of circles or surface elements, oriented disks, to represent space. The other approach is to use a volumetric representation, such as the TSDF, or truncated sign distance function. A volumetric representation means that the data structure represents volume, in a way dividing up the space. Using a list of circles as the geometric representation comes with certain trade-offs. One of the greatest benefits of using circles instead of a volumetric representation is the avoidance of the redundant work that the TSDF needs in order to function. Other benefits include the malleability of the circles. As the SLAM is constantly optimizing its estimations, circles can be moved around at will much more easily than data inside a TSDF. However, this comes at the cost of being less robust to noise, as well as no longer obtaining manifold meshes. The redundant work that the TSDF needs is depicted in the diagram here. Notice that there are two data structures when running SLAM and 3D reconstruction side by side. The SLAM requires a keyframe map in order to perform its localization. The 3D reconstruction requires a TSDF, in which we integrate new frames into and extract a mesh from. Using a list of circles, we wouldn't need the 3D reconstruction data structure and could use the keyframe map and an additional list of circles both for SLAM and for 3D reconstruction alike. The TSDF operates as follows. First, divide the space evenly into voxels, or volume pixels. You can think of them as small cubes. Second, retrieve a pose-estimated depth image and project its pixels into a 3D point cloud. These pixels all lie on the surfaces of objects. Depth measurements are taken of surfaces, and empty space has no measurements. Third, for each point, draw the ray from the camera to the point. For the voxels along the ray before the observation point, assign a positive value representing the distance to the point measured. For voxels along the ray after the observation point, assign a negative value representing the distance past the point measured. In this representation, when voxels change signs relative to their neighbors, this indicates a surface. As we take more observations, we average out the value of the voxels. In this manner, we can minimize the impact of noisy measurements as each voxel becomes the average of many different samples. Another benefit of TSDF is its performance. Integrating frames with one another happens extremely quickly, enabling real-time 3D reconstruction. Once the TSDF has been filled with observations, a mesh can be extracted. The predominant mesh extraction algorithm is called marching cubes. Marching cubes is an algorithm developed by Lawrenson and Klein in 1987 and uses the following technique to generate a mesh from a TSDF. For each voxel, calculate the plus-minus value of each vertex, where plus means outside an object and minus means inside an object, and perform a lookup based on the combination of the 8 vertices for the appropriate pre-computed mesh segment. There are only 2 to the power of 8 possible configurations for the vertices of a voxel, and many are rotations of others. The major benefit of using marching cubes is its speed, as it only requires 1 lookup per voxel and no other calculations. However, it results in a blocky texture similar to that of Legos, hence the name marching cubes, due to the nature of the algorithm. This is counteracted by later steps of simplification, as well as increasing the resolution of the reconstruction and decreasing the size of the voxels. When simply generating a reconstructed mesh, the complexity of the mesh becomes very large very quickly. For reference, this small section of my house, recreated on the left, has over 4 million faces. For comparison, this scene from Crysis 3, one of the more detailed video games of the past decade, has only 3 million triangles. The reason behind this is the existence of many, many small triangles that are simply comprising a larger plane. This is due to the process in which our mesh was created. Each voxel, each small cube of space, generates anywhere from 0 to 5 triangles in our final mesh. Clearly, there is some redundancy there. For example, the wall of the hallway in the left image is basically a rectangle in 3D space. This can ideally be represented by only 2 triangles. 2 techniques to reduce the complexity of a mesh are quadric edge collapse and planar extraction. Quadric edge collapse seeks to reduce the amount of faces in a mesh by removing edges and merging faces that reduce the error in the mesh the least. This iterative approach can extract a simpler mesh without too much trade-off. For specialized cases, such as the hallway in the previous slide, planar extraction is a useful mesh simplification technique. The goal of planar extraction is to detect planes in a point cloud, and using this data, we can assign a few large triangles to represent the entire plane. Mesh texturing further optimizes the use of the mesh in applications, easing the process of rendering a mesh. Texturing is the process of mapping each point on the mesh to a 2D coordinate and then saving the mesh colors onto a 2D plane to be used later. Although not relevant to real-time reconstruction, for incorporation of a mesh into a scene, texturing is very important. One of the biggest hurdles to overcome in 3D reconstruction is the ability to perform the reconstruction in real time. With long computation times and endless memory, offline reconstruction is an art on its own and can be optimized to the point of perfection. However, in real-time 3D reconstruction, trade-offs have to be made for speed and memory efficiency. With real-time reconstruction, new frontiers of AR can be explored. One such application is HoloLens holoportation, Microsoft's technology that brings live 3D reconstructions of people into your living room via the HoloLens. An array of sensors takes measurements of one person and performs 3D reconstruction, sending it to another person's HoloLens, allowing them to interact as if they were there. When dealing with real-time 3D reconstruction, we run into the issue of scalability. When performing offline reconstruction, once the data has already been collected, the extent of the reconstructed scene can be calculated beforehand. During real-time 3D reconstruction, the system must be able to scale indefinitely. In order to achieve this, we perform several upgrades on naive TSDF. One major weakness of traditional TSDF is the issue of rigid space allocation. Because we divide the real scene into voxels of fixed side length, we must decide the overall dimensions of our scene upon the creation of the TSDF data structure. One possible solution for this problem is a hashing function that assigns a value to sections of the real scene, each containing multiple voxels. Each one of these sections can be thought of as its own TSDF. In this way, the scene can grow dynamically as more parts of the scene are discovered and placed into the hash table. This allows a much more efficient and scalable TSDF representation. The implementation we use is derived from the elastic reconstruction system. Another solution to the scalability of TSDF is mesh blocking, where every time the camera has moved a certain distance, a mesh is extracted and the TSDF is reinitialized with the current camera position as its center. In this way, real-time reconstruction can be extended much longer. However, with the drawback that earlier sections of the mesh are now immutable. This also helps with speed, as the size of the TSDF we keep is limited, and we only need to render the older blocks of the mesh. The attachment between blocks of mesh and keyframes is key to the speed increase and malleability of the real-time reconstruction pipeline. The rendering process of previous mesh blocks includes a step that checks each keyframe's position and location, estimated by the SLAM system, and transforms the mesh appropriately. As SLAM continuously optimizes this pose and location, the mesh blocks align more accurately with the real scene. Just as with SLAM, we will peer into OpenArc and see what allows the system to run and provide both real-time and offline 3D reconstruction. In addition to the open source libraries required to run SLAM, which is also used during real-time 3D reconstruction, Open3D is another open source library used for OpenArc. The specific functionality provided by Open3D are the TSDF, the data structure used for integration of camera frames, mesh extraction, the implementation of marching cubes, and voxel hashing, the spatial hashing function used to expand the scalability of TSDF, as well as improve its speed. The SLAM dependencies are also listed here for convenience. The frame data types used in 3D reconstruction are the map keyframe, multi-camera frame, and RGBD frame. The first two are used for input and output to the SLAM system of OpenArc. The final frame data type, RGBD frame, is used for integration of frames into the TSDF. The main workhorse for OpenArc real-time 3D reconstruction is the segmented mesh object. It handles all the functions required for reconstruction: integration of new frames, extracting the current mesh, and performing the mesh blocking algorithm described in earlier slides. Integration of new frames is implemented using the voxel hashing algorithm powered by Open3D. It is run on the CPU and sped up using parallelization provided through OpenMP. Mesh extraction uses the marching cubes algorithm to quickly retrieve a mesh from the current TSDF. In accordance with the mesh blocking algorithm, there is one TSDF data structure maintained at all times. Along with this is a vector containing immutable blocks of older sections of the mesh, each capable of transforming independently when loop closures optimize older parts of the map. Another important class for OpenArc's 3D reconstruction module is the Save Frame class, used for saving data in order to perform offline 3D reconstruction. In order to perform offline 3D reconstruction, 4 pieces of data need to be saved: an RGB image, a depth image, the pose estimated for the frame by SLAM, and the camera intrinsic, required to project the depth image back to 3D space. This saving of data is crucial to the philosophy behind OpenArc's real-time 3D reconstruction. One of the limitations of real-time reconstruction is the rapidly increasing computation complexity when the resolution of the mesh increases. For consideration, a room constructed at a resolution of 1 centimeter may have millions of triangles, while the same room reconstructed at 3 centimeter resolution may only have 10,000 triangles, a much more reasonable number to render and integrate to in real time. Also, in real-time reconstruction, optimizations to earlier portions of the mesh arising from loop closures are difficult to deal with, and oftentimes expensive operations are required, such as de-integration and reintegration of all previous frames. Therefore, OpenArc's 3D reconstruction module is broken up into 2 parts, an online and an offline part. The online part runs real-time reconstruction at a lower resolution with the goal of providing the user a visualization of the current scanning progress. The data is saved at the same time, and then the scene can be constructed at a very fine resolution once SLAM has stopped running and the poses have been finalized and optimized as well as possible. The real-time 3D reconstruction demo has the following structure. As with the SLAM demo, first, we initialize a camera object, specific to whichever camera we are using to run OpenArc. Then, the SLAM system, segmented mesh, and GLFW manager objects are instantiated. Callback functions should be passed into the SLAM system. Then, the main loop can be run. When the output of SLAM is received and a pose has been estimated for a new frame, it is passed into segmented mesh for integration. It is also passed to SaveFrame for saving, to be reconstructed later offline. Loop closures are also detected from the SLAM system, and the transformation of older mesh blocks inside segmented mesh are updated accordingly. The following screen captures are the results from our real-time 3D reconstruction algorithm. The code was run on a Microsoft Surface Pro tablet, and the scene was captured in one cursory pass using a single RealSense D435i camera with stereo depth and an RGB camera. The reconstruction required real-time integration, mesh extraction, and rendering. The data was also saved for later offline reconstruction. The integration is run at 10 Hz, and the mesh extraction is run at 1 Hz. One thing of note is that since the 3D reconstructions come from a single RGB camera, gaps in the scene are inevitable unless one is extremely careful about their scanning technique. Also, the backsides of objects in the scene will inevitably be incomplete as they are fully occluded. These screen grabs here depict the difference between real-time and offline reconstruction quality. The image on the left, taken from a 3D reconstruction run at a resolution of 3 centimeters, exhibits many of the weaknesses of the Marching Cubes algorithm. The surfaces of the scenes are very blocky and have imprecise geometry. The image on the right, taken from an offline 3D reconstruction run at a resolution of 0.5 centimeters, shows the effect of simply increasing the resolution of the reconstruction on the performance of Marching Cubes. For comparison, the image on the left has 10,000 faces, and the image on the right has 9 million faces. In regards to the gaps in the scene due to imperfect scanning, the solution is the study of object completeness. Recent works, such as this paper, extending deep SDF for automatic 3D shape retrieval and similarity transformation estimation by Oladapo Afolabi, a previous PhD researcher at the Berkeley AR/VR lab, have explored the use of deep neural networks to learn how to fit complete models to incomplete objects in the scene, filling in the gaps that are left due to imperfect scanning. Some future work at OpenArc involves having some fun with 3D reconstruction and seeing where it can be applicable. We have a team working on performing real-time reconstruction on drones, which would require large engineering improvements and considerations such as bandwidth and computing power on board the drone. Another struggle is the performance of depth, both at great distances over 10 meters and the lack of IR capability as the sun blows out all IR light. Now that we've built a foundation, finally, I'll provide a quick guide on how you can get started with OpenArc today. OpenArc's source code is hosted at the link here on GitHub. Updates to OpenArc are pushed to the master branch of this repository. Feel free to make issues or pull requests here to join the OpenArc community. The first step towards using OpenArc is installing dependencies. OpenArc has a lot of dependencies, and each needs to be compatible with one another, as well as OpenArc itself. The recommended way to install the dependencies, if you are using Windows, is via the Windows Dependency Installer. The link to the .exe file can be found in the project README. This installer will install the binaries to a folder and place an environment variable pointing to the folder such that OpenArc can find them. You may need to add the bin folder to the system path manually if you are running OpenArc from a non-primary user on your Windows computer. If this dependency installer doesn't suit your needs, or you are building OpenArc on Linux, you need to either build from source or on Linux, obtain the dependencies via your package manager. The instructions for this are under the documentation folder in the repository. OpenArc is built using CMake, an open source build tool available on most OSs. Specific instructions to build OpenArc are included in the documentation. Inside CMake lists.txt, certain build options can be toggled, such as build hand demo, build avatar demo, and build slam demo, to influence which demo files in OpenArc are compiled. The demo files will be compiled and the output executables will be placed inside build/release. Including OpenArc in your own projects is easy with CMake. Simply add find package OpenArc to your CMake lists.txt, and the library functions will be ready for you to use in your own project. Two of our high school interns, Advit Deepak and Michael Peng, put together an OpenArc installation guide video, hosted on YouTube and featured on our main repository. It'll help ease over the process and deal with many of the common issues with installing OpenArc. Finally, feel free to check out the other demos inside OpenArc. OpenArc is not just limited to 3D reconstruction and SLAM. There is functionality to track hands and avatars, as well as code to integrate OpenArc with Unity, although that is currently in progress. Thank you for listening.
Hello, everyone. I'm Mohammed Kishvarzi. I'm a PhD candidate at UC Berkeley. I work at the FHL Vive Center for Enhanced Reality and also the XR Lab. And today, I wanted to talk about how generative modeling and its applications can benefit future spatial computing experiences. Okay, so let's start. So as you all know, spatial computing has emerged as a promising platform for next generation human computing experiences. And it's hopefully going to change our lives and the way we interact with computational systems. The way we play games, the way we communicate are all things we're looking forward to in the spatial computing era. Now, when you think of it, it's not just that spatial computing allows us to see things in 3D instead of a 2D screen, but it actually is some kind of a connection between us and our surrounding environments and virtual environments. So it really gets us closer to the objects and other entities around us. In other words, spatial computing experiences executed on the grounds and the context of our own environment. All the geometry, the structure, and all the functional relationships present in our own environment make up the visual foundations for spatial computing. And as I said, there's a very extremely exciting body of work going on in the field of telepresence. In other words, sharing spaces or bringing other people to our own spaces is really going to change the way we all will communicate. And hopefully spatial computing would play an important role in future telepresence workflows and understanding how these systems will interact with people and their individual spaces. It's a key step in the direction of utilizing this technology in future communication systems. Okay, so when we're talking about spaces, it's really important to keep in mind that our surrounding spaces are very different from each other, both in terms of their geometrical properties, such as size, layout, and material, and also the functions they serve. Yet, when we think of future AR applications or mixed reality applications or even VR applications, one of the main challenges that can be highlighted is that there is somehow a design barrier between the content developer and the users. So what do we mean by design barrier? Well, content developers are not aware of the exact properties of our rooms. So when you're a spatial computing developer, you really don't know what and how your content will be displayed in the context of other people's rooms. So you don't know that, the experience and the development you're doing, how would it show up and how would it look like, and reflections and colors and materials. And these are all unknowns to the developer and the content designers. We also had this a similar problem before when we were trying to develop one type of content for different screen sizes, for different target devices. So right now, websites use a technique called responsive design. You write one set of code, but it's basically responsive to different screen sizes, different resolutions. And we might think, spatial computing can also go in that way. But the problem is, 2D screens come with a lot of difference between, what really is in our 3D environment. There's 2D screens, it's just some rectangular, black, empty screens, while in 3D, we have this very irregular geometries happening around us. There's so much ups and downs, and there's so much obstacles that it's not that easy to predict and lay out the content way before actually seeing and analyzing the scene. And of course, the technology to fully understand the scene and its geometrical property, the very high quality mesh extractions, the semantic segmentations, what functions and how they work together, we still have a long way to go, and there's a lot of challenges to kind of overcome. So in general, that's what we're talking about, the design barrier between a developer and our spaces. And if we don't come up with a system in between, it's going to be pretty hard to actually solve this issue. So what's really important is not only that we need to think about how one single content developer or a company wants to develop for our spaces, but going back to the discussion of having mutual telepresence experiences, even individuals, even users of spatial computing experiences would have issues in communicating together when they don't know and are not aware of each other's spaces. So today, with a focus on generative modeling, I really want to talk about the concepts of, can we come up with a way to contextualize our virtual experiences in the spatial computing platforms. So I'll try to cover two directions of this topic. First of all, content augmentation, and also mutual spaces for users that are connecting remotely and are not aware of each other's room. So let's start with a content augmentation of unknown target scene. Let's open this problem a little more. Say we have a target room of a user. On the left, you see a top view of its living room, and on the right, we see an eye-level perspective view. And for our spatial computing experience, we want to add a virtual object or a specific content to our physical room. And for the sake of example, and just to show some meaningful relationships, let's just say we want to add this chair to the target room, okay? So as you see, the main challenge is, in theory, the chair can be placed anywhere in the room, in any direction and any location, which may cause some geometrical conflicts. And even if it's not causing some conflicts, it may not be placed within the suitable context. So you see examples of what I just mentioned here. On the left, you see the chair is conflicting with other chairs and sofas. And on the right, you see it's inconsistent with the context. It's just looking in a direction that you would never generally place a chair like that in a room. So let's talk about a little background of how others have tried to address this problem. In general, we have two main strategies for addressing the scene augmentation challenge. One is coming up with a procedural model, and two is learning from prior examples. I'll talk about in detail of what each of these means. So let's start with procedural modeling. So procedural modeling, we can just define it as rule-based modeling. Okay, so any kind of automatically generated asset based on a limited set of user-defined input parameters can be defined as procedural models. Okay, so we come up with a set of rules. These rules can be hard-coded in the system, or it can actually have a user in the loop. So let's see some examples. Okay, so this work was published by Tobias and Schwartz in the Computer Graphics Forum in 2009. And it shows how an agent-based procedural model is utilized for each object to find suitable parent objects and to place and orient itself properly. Okay, so the agents are given the object size, its bounding box, the class of the possible parent objects, and basically everything they need to know to find what the best parent and the best position in relationship to the parent can be. So in other words, the ideal relationships between the objects are hard-coded, and the system goal is to find the best arrangement possible to achieve a higher number of acceptable parent-to-child relationships in the scene. On the middle, you see the generated tree graph of the system, and on the right, you see some results of their system. So when we move forward, we see another study here by Paul Merrill and his colleagues that utilize procedural modeling again for synthesizing scenes and generating plausible scene alignments. This work was published at ACMTOG, and over here we see, in addition to very straightforward relationships like object adjacencies and parent-to-child relationships, the authors have actually hard-coded functions such as circulation scores, conversation possibilities, visual balance, alignments, and these kind of qualities. And these are basically some of the rules interior designers intend to implement in their designs. And the authors have basically extracted these qualitative rules from textbooks and translated them into some sort of quantitative embodiment in a procedural code-based fashion. But with looking at these two studies, which are honestly just examples of many other papers which utilize procedural modeling for generating environments and scenes, with all the success they've shown, the results typically differ from a naturally arranged scene we really see in real life. And we can attribute these differences, to two main reasons. One, design is generally considered a high-dimensional task. So what do I mean about high-dimensional tasks? It's like you just don't want to achieve one goal in this process, right? There's multiple different goals that come up in the design process, and you want to basically approach them all together. And the human designer, is responsible for prioritizing them. That's why you see so much different designs, and some designs have a strong aspect in one criteria and some don't. Now, if you give this to a system, you have to do the prioritizing for them. And it's not always easy. And many attributes may cause conflicting arrangements with each other. So many models end up defining weights and arbitrary prioritizations, which cannot be generalized in many cases. The second drawback is, the systems cannot capture those very small, unique natural qualities. These qualities generally emerge in the process of time and human engagements. People refer these qualities to qualities without names, and it's really absent in such models where everything is rule-based and hard-coded. So this takes us to the second method. And the example-based modeling method, or the data-driven modeling method, has gained a lot of momentum in the past few years. In these set of methods, instead of hard coding a set of procedural rules and patterns, we set examples for the system and expect the system to learn from them. Okay, this way, we're not bound to a set of discrete rules, and we don't need to arbitrarily weigh and prioritize between them. So this is one of the early successful papers, also published in ACMTOG by Matthew Fisher and his colleagues at Stanford. The idea is pretty straightforward. You give a set of example scenes as input to the system, and the system starts synthesizing new scenes, very similar to the example scenes, by learning from the relationships and constraints from a set of prior scenes. Okay, so you have like some input scenes, the system starts modifying them using the constraints you see here in the middle from a database, whole other sets of scenes. What they do is they just develop two probabilistic models for one, object relationships, and also an occurrence model, basically knowing that what object should be added or not added to the scene. So the first one, again, it's helps to understand what object should be available in this generated scene, and the second arrangement model is basically where those objects should be placed. So in addition to coming up with probabilistic models for object arrangement and also occurrence, there's also another very interesting direction that has been introduced in scene synthesis literature that also taking into account human activity. And this is very interesting when you look at it in data-driven generative models. For instance, this work again by Fisher and his colleagues start with a 3D scan and learn the scene template that describes different activities that can take place in environments and generates kind of a rough geometrical layout of the scene. So you have two representations: one, the rough geometrical layout, and also an activity map. Based on these two trained models, you can generate new synthesized scenes that respect the activity and geometrical constraints of the scene template. So in addition to pairwise relationships between objects, right, you have a human activity also involved in the training of the system. Okay, so the question comes in, like, what data sets people use for this? And I'll try to define these as three types. One, we have synthetic data. There's a data set, actually, it's kind of in a dispute situation right now, but it's called SunCG. There's around 45,000 human-generated scenes extracted from a website called Planner 5D. And basically, people have gone on that website, tried to design their own homes, and this is being used as a data set. There's a lot of discussion whether this data set can be really a good sample set for training data, and we'll talk about this later. But it has a lot of data points, so it's really helpful for approaches like deep learning. The second type, which is kind of emerging set of data sets, is also fully scanned homes, and you can imagine how hard it is to kind of scan all these scenes. The Matterport 3D is a very good data set in this regard. There's a bunch of other data sets, but I guess the probably best open source available data set right now is the Matterport 3D. You also have, some new work. I brought an example here, like PerspectiveNet, a 3D object detection. So you give a RGB, and the system actually extracts the bounding boxes, and it comes with some level of accuracy, but in general can be really useful in our field of scene synthesis and really understanding the relationship between objects. So given that background information, I wanted to quickly go through a recent study of ours and how we approach the problem of scene augmentation using scene graph writers. So again, same slide. We have a spatial scene representation. A previous semantic segmentation system would help us understand the semantics and the bounding boxes of our objects. So this is a given in our system. And once we have these bounding boxes, we allocate each object to a node and their relationships as edges of a graph. And these relationships can be positional and orientational. So it's like how two objects are related towards their position, whether it's an edge of the room or it's in the middle of the room, or are two objects close to each other, or whether it's facing, whether it's towards the center of the room, or similar directions. We extract all these information from the objects in the scene and generally come up with a spatial representation graph that describes all the topologies happening in the scene. Now, the idea is when we start exploring the different positions a new object can be placed in, we generate new scene graphs for each instance. And our system is able to find the highest probable plausible scene in all the kind of sample positional or orientational points we have. And the question comes, how do you come up with this probabilistic model? Well, we train it based on a previous knowledge model. So we go through all the, our training data set in the Matterport data set, and we extract the scene graphs from it. So once we have the scene graphs from our data training split, we come up with a knowledge model that basically guides our probabilistic models for understanding which layout would be the most plausible layout in the samples. So going back to the data set, yes, we use the Matterport 3D data set, and there's a lot of discussions of why we did this. Again, we talked about those natural design occurrences that really happen in the integration of time and human activity. And you see this really happens in our real world environments. And synthetic data sets typically don't capture those environments. Even data sets that are generated by human designers, not just like ordinary people, but people that are, for instance, architects, tend to have a lot of difference between what they were initially designed and what they end up to after people living in them. So it's really important to kind of have that in mind. Okay, so here's also a visualization of all our relationships in both positional and orientational features in our data set in the Matterport 3D. And you do see some interesting observations over here. For instance, the bed is usually towards the center of the room. Over here, you see on the left, you see the storage is typically in the corner or at the edge of the room. It doesn't really happen to be in the middle of the room. And in general, we're trying to really show this kind of a visualization of our knowledge model. Okay, so let's show how our system works with a bunch of experiments. We have an empty room over here. This is the top view. We can extract the spatial representation graph, the scene graph, which we discussed from this target scene. And when we want to add a bed, we can basically sample the whole room, the possible positions, and visualize a probability heat map. Over here, you see the darker the red, the more probable the object can be in that location. And also here, you see radial visualization for the orientation probability. The greener, the higher chances that the bed, when placed there, would be plausible. So if we go through those two models, the placement model and the orientation model, we can place the bed over here and you see the perspective view. Over here, we have a chair that we want to add, a bed, a desk chair, a coffee table, and also a kind of drawer, all placed in pretty plausible placements. We can also look at how we can place multiple set of objects. Over here, say we want to add a bed, drawer, and a sofa to the room. Same process, we can generate the heat maps. And as you see, when we augment the objects to the scene and we compare them to the ground truth, we do have some interesting observations. The bed, for instance, is placed in slightly different position, but again, it's still plausible. It's probably finding some relationships with the drawer on the left, but still you see the scene synthesized on the left can be totally possible and totally plausible from a user perspective. Here are some other examples. When we compare with the ground truth, the top row, we see a pretty similar arrangement. The row below, we added another coffee table in addition to what was already in the scene. And again, we see some plausible results. Okay, so in addition to qualitative experiments, we also come up with how we want to evaluate our system in a quantitative fashion. And this is a very interesting question you need to ask in any kind of research project, that what's the best way to really show the strength and weaknesses of your system with a set of experiments that kind of can be also compared with other systems as well. This is an experiment that we're doing. So given a ground truth scene, we take out one object. That scene that the object is being removed from will be served as an input to our system. And we would like to place the object that we removed from inside the scene. And so once we've placed it, we compare the distance error between our augmentation and the ground truth. So here are the results of the experiment in an ablation study setting. In our ablation study, we observe how the system performs with the presence and absence of different features in our proposed scene graph representation. On the left, you see the cumulative distance error between our top prediction and the ground truth. And on the x-axis, we have the distance in meters, and on the y-axis, we have the percentage of the scene augmentation instances falling below that error threshold. The right figure holds a similar setting, but this time, instead of comparing the ground truth with our top prediction, we compare the ground truth with the closest of the 5 positions. And the reason we use top 5 is exactly as we mentioned, since the object augmentation may have multiple correct plausible solutions, we would like to make sure we don't limit our evaluation to only the top prediction. So in addition to numerical experiments, it's also informative to basically ask users what they think. And this is the way we kind of designed our experiment. So if you have our original ground truth, again, in our case, because we're using Matterport 3D data, we took scenes from that data set. And we reconstructed the whole thing in Unity. So it's like a simplified reconstruction. Now, we designed 5 levels of our reconstructed scenes to randomly be shown to the user. The first level is when we place an object just randomly in the scene. Okay, so over here you see some probably geometrical conflicts and strange topological relationships happen. In level 2, it's the same random position, but only in open spaces. So we avoid conflicting geometries, but the system won't come up with a plausible way to really show the relationships correctly. Level 3 is SceneGen, our approach. Level 4 would be our approach with a heat map, and level 5 would be the ground truth. And so we randomly show these different levels to the users. And here's our user interface of how they interact with our experiment system. Basically, they click on add the furniture, and when the furniture is added, they just give a score from 1 to 5 of how plausible the furniture placement is. So here's some results. It's pretty promising. You see that people aren't giving very good scores actually to level 1 and level 2 because random placements, and they weren't looking really good. You see a pretty small difference between our system and the ground truth. I guess this shows that our system is generating some plausible scenes in the masses and in the perspective of our participants of our user study. Now, we can also compare SceneGen with the ground truth, not only in terms of the general placement, but also by object category. We do see over here, for instance, the chair in SceneGen may not always work as good as the ground truth. Turns out, it's more of a subjective matter how you place a chair, because, there's probably a lot of possible and even better placements that users thought could be placed than the ground truth itself. So in addition to asking the user participants to give a score from 1 to 5 to the plausibility of the scene, we also asked them to actually adjust the augmented objects to a position that they thought it would be better. You see this plot in this figure shows the distribution of those adjustments by the users in red, and the distributions of our top 5 predictions in green. What we're trying to kind of say in this figure is, again, it's not just one position that would be the ideal position for different objects to be placed in the scene, and there can be multiple regions in a given scene for that object, and SceneGen in some cases is doing a pretty good job in capturing those, and we can see those regions also captured in users' preferences in the scene augmentation positioning. We also develop an augmented reality application for this system. The idea is, if a user wants to augment an object in a scene with our system, it would be much more easier, much more faster, and more awareness of the spatial relationships of the scene itself. So in this video, you see first of a manual placement without our system. It takes some time for the user to come up with the best location and position of these certain objects that can be accessible through the menu of the augmented reality app. And compared with our contextual placements in this video, you see these heat maps basically showing where the objects can be placed. Okay, so we talked about how content augmentation can happen in spatial computing experiences. Now let's talk a little bit more about the concept of finding mutual spaces. Okay, so this work called holoprojection developed at Microsoft Research is one of the many great examples of how mutual space can be preserved in augmented Hello, everyone. I'm Mohammed Kishvarzi. I'm a PhD candidate at UC Berkeley. I work at the FHL Vive Center for Observed in Augmented Reality, or any general spatial computing setting. Look how the presenter here, Shahram Izadi, steps back from his ground to allow his daughter to move around the table. I was personally very inspired by this work the day I saw it back in 2016, and it illustrates a very bright future of how telepresence systems can be utilized for remote communication. But if we pause the video for just a second, we do see some critical issues. First off, the amount of space allocated for this experience in both rooms is pretty large. And if we look closer, we see some markers on the floor indicating that objects of these rooms, the chairs and the table, were manually calibrated beforehand. But those settings may not really be feasible in our everyday environments, right? To have large and accessible open spaces without any obstacles, and each time manually calibrating our surrounding furniture with each telepresent participant without actually knowing how other spaces of those participants looks like. So it's fair to say, with our current real world environments and surroundings, collaborative spatial computing has spatial limitations itself. So let me open this up a little more. Say we have three individuals wanting to hold a remote telepresence call with each other. User A in red, user B in yellow, and user C in blue. So user A resides in this very large living room. You can see a perspective view on the left and a floor plan view on the right. User B, however, wants to join the telepresent meeting in her small office. And user C is working from the home, to planning to meet in his bedroom space, which has a little bit more open area for the others to join, okay? So let's look at the first problematic scenario. Okay, so this is user's A room, and he's hosting the meeting, which augments virtual avatars of user B and user C in an open area of this pretty big living room. With holding the same positional relationships with each other, in user's B space, however, she actually sees no one, basically no one. But if you look at the floor plan view on the right, the other two gentlemen are located outside her office. You see, when keeping the same positional relationships with each other, initiated in the previous scene, they just don't fit in user B's office. And more weird things happen in user C's room, where user A is looking like a ghost stuck in the wall and the dresser, while user B is also colliding with the furniture. Both remote individuals are in undesirable locations. Now, you may ask, why do we need to keep the positional relationships constant? Why can't users have the option to force position and manually identify a desirable location for the remote avatars to be augmented in its space? So let's see what happens. Here we have the participants holding constant relationships with each other in all rooms. Now, let's just allow them to manually force position remote avatars in their own preference to kind of fit in their spaces. So here's the problem. When user A is looking and talking with user C in his own room, shown on the left, in user's B room, shown in the middle, the direction user A is talking to the wall, and the line of sight is incorrect. And this becomes much more abnormal in user C's location on the right, where user A is supposed to be facing at user C, but instead is looking at user B in a complete other direction. So, how do we address this challenge? And this is where our contribution kicked in our study of optimizing mutual spaces. Our first goal is to locate where users can walk and talk in their own room without colliding with objects in other remote rooms. We kind of do this by finding the mutual space between all the rooms. So let's see how that works. Say we have 4 rooms, okay? With 4 individuals planning to remotely meet each other in a spatial computer setting. First, we perform a semantic segmentation
Exactly like the previous study, we consider this as a given to the system to basically determine the bounding boxes of each object in the room. Next, we intend to locate standable spaces. And standable spaces are basically the volume of the room in which no object located within a human height range is present. Okay? And the user movement can be performed freely without a risk of colliding with the object in its surrounding physical environment. We calculate the standable space by simply subtracting the area of which the object occupies in a room from the room itself. Okay, so we do this with all the rooms. Next, we define a rigid body function G, where theta describes a transformation vector. We then run a genetic optimization to determine the optimal theta of each rigid body motion. So the area of the overlap between the boundary becomes maximum. If we map the mutual space back into the rooms, shown here in the blue area, when all the users stand or walk within the blue area in their own spaces, they are guaranteed not to cause virtual conflicts or line of sight mismatches within each other's spaces. Now, to add a little more flexibility and increase mutual usable spaces, we can also define sittable spaces. Sittable spaces normally extend the standable spaces by adding areas where humans are able to sit on, such as sofas, chairs, and beds. Again, if we go through the same process, this time with sittable spaces, we observe larger mutual areas, okay? Which users can stand, sit, and walk and move around all those spaces without actually worrying to cause any unwanted collisions in other remote rooms. Okay, so we wanted to implement our proposed framework on some real-world data sets just to see how that works. And again, a Matterport 3D data set from scanned real-world data set is the one we chose. And over here, you see standable spaces are indicated in green and non-standable spaces are colored in red. And in this figure, you see sittable spaces are also visualizing yellow. Again, this is the calculation from the system. Moving on to identify the mutual space between these rooms you see in the figure, we kind of show how our genetic algorithm is gradually improving the results and expanding the area of the mutual space. And in higher generation values, we kind of see that this blue color, this blue space, it is generated after 40 generations of the search between these rooms. But here's the thing. What if we want more mutual space? What if it's just not enough? And the identified mutual grounds are too small for the remote communication purpose. Say you want to play a game or inspect an object between participants. Where the object doesn't fit in the mutual boundary, can we move it? What do we do? That brings us to the second goal, which is, can we rearrange the furniture so that we increase the mutual space while minimizing the overall effort to do so? And the effort of each move is basically calculated by multiplying the distance of the object's transition by the object's width. So in simple terms, moving a bed is considered to have a higher effort value than moving the chair for the same distance. So again, our goal is to slightly manipulate the room layout to increase mutual space with minimum effort. And to simplify this process for the user, we kind of define some increased steps, which each step has the goal to achieve 10% additional mutual space from its previous step, while maintaining the minimum effort to do so. Now, let's take a look at the furniture manipulation system on a set of Matterport rooms example. Again, we have real-world scenes. We have a family room, an office, and a bedroom. And first, we extract the standable and non-standable spaces using the methods we kind of previously explained. And by utilizing our proposed mutual space identification system, we can locate the maximum mutual ground between these rooms. We then use a strength Pareto evolutionary solver basically to optimize for the two objectives. effort, which is shown in this vertical axis, and the mutual area on the horizontal axis. Okay, so when we plot the rearrangement solution space, we can find the initial arrangement point of the Pareto frontier with the e-value of 0. Okay, so the effort is 0, and this is our mutual space without moving any furniture. Then, by increasing 10% of the area in each step as a goal, we start to find the rearrangement solution, which satisfies the increased area goal and holds the lowest effort value in each step. So we're basically moving towards increasing the area while we're trying to minimize the effort to do so. So as you see over here, after 5 steps, we kind of show a significant increase of the mutual space while trying to minimize the effort required of the furniture rearrangement to do so. Okay, so the whole idea was for augmented reality telepresence. At that time, we didn't have, the techniques to do avatar telepresence, but we kind of tried to show a better understanding of how the users would experience the system's output by deploying our proposed method with the Microsoft HoloLens on augmented reality visualization. So for the target spaces, we scanned our office area at Corey Hall. All this happened before the pandemic hit. And in our office area, we had a conference room, a kitchen, and a main lab space for our experiments. We also provided the bounding box and semantic labels for the model. So we scanned them and basically labeled them. We then give this data to our system, and the system calculated the open spaces visualized here in green, and the mutual spaces also visualized in blue. And these are kind of the captures we have from the HoloLens in the kitchen. You see the mutual space boundary is with an offset of 40 centimeters on the ground, so users can clearly relate to it. And here you see the main lab in Corey Hall. The blue indicates the space that you can freely move around this boundary without causing any conflicts in the other rooms. Okay. Finally, a floor plan view of the space with different screenshots taken in different locations of the HoloLens headset. So of course, there is limitations to our work. First off, in our current version, the increase in steps may not have any continuous relationships with each other. For example, in step 1, you might be moving a chair in a certain direction to achieve minimum effort, but if you then decide to move to step 2, it doesn't take into account steps 1 transformation. The next limitation is that our current system doesn't automatically take fixed positioned objects into account and should be defined manually. We also currently use generic data provided by moving companies to estimate the weight of an object, given its type. However, objects from the same type may have various weights, and therefore, it would be important to integrate correct values to achieve more accurate results. And finally, our future steps. We definitely want to perform more extensive user studies. We also hope we can develop this tool for cross-platform AR/VR interfaces and also use more robust floor planning methods for the furniture manipulation. And that's it. Thanks very much for listening and tuning in. Please feel free to contact us with any questions you have. We would be happy to connect with you guys and answer anything we can. Hope you have a very good day. Bye-bye. Hello, everyone. I'm Mohammed.